In this video, we'll move into section 5.3, which will cover our second technique for finding volume. This specifically will be what the book calls the cylindrical shells approach. I informally just call this the peeling method. But just before we jump in, and we're going to do just like we did with our first technique, we're going to start slow, look at some pictures, and try and get some understanding before we get to work. We're certainly going to do that here, but I just want to take an extra minute or two to go back and look at what I called the chopping technique. Because this is called cylindrical shells, but both techniques really focus on an ideal figure, which is a cylinder. So that if I just draw two perfect cylinders, and cylinders, we're thinking of soda cans. So if I have two cylinders, this one is an upright cylinder, and the second cylinder is on its side. So we have two different cylinders. The whole idea of our first technique is to, again, literally think about taking out a big meat cleaver and literally chopping or sawing these pieces, to saw them into smaller pieces and then adding up the volumes of each of those subsequent smaller pieces. But all of those pieces, they can't be random, irregular cuts. They have to still be something that's giving you that little piece of cylinder. So now ours weren't perfect cylinders. We had shapes more like this. So maybe this is more of like an instrument, like some sort of a horn where your mouth is on this side and it opens up this way. And whether this is actually filled in or not, that's irrelevant. But this is similar to this. If I have this perfect cylinder, if I cut across through the roundness, and in this picture, this would have been generated by revolving around this axis. So if I make those chops across that axis of revolution, each of these would still be perfect cylinders, they'd just be smaller perfect cylinders. Again, take that soda can, put it on its side, and think about doing this, and you'd have three of those smaller cylinders. Now, if it's a soda can, this side and this side, this still has a top, this still has a bottom, whereas all these cuts, these just be open space, but that gives you a good picture, something to visualize. If you do that same thing over here, well, you don't get perfect cylinders, but you get those still perfect cylindrical pieces. If you tried to cut this one horizontally, you would just get a bunch of odd random chunks. So again, you'd have to cut across the axis of revolution, across the direction that is giving us our roundness, and now we don't get those same perfect cylinders we have here. This is a little bit bigger than this piece. This cylinder is a little bigger than this. It's not even a perfect cylinder, right? We'd have to flatten out these two sides, but that was the idea, that we're not just making 3 or 4 cuts. Technically, we're making an infinite number of cuts. But this is still very worthwhile if you're still having trouble visualizing, and as we move into a second technique, realizing when you're using each technique. I'm hoping this helps, because now come back to this first one. In this first one, it's still that nice perfect cylinder the same way this one was, but now which way do you have to cut? If you still make vertical cuts the same way we did here, then you're not going to get nice cylindrical pieces. You're just going to get random misshapen pieces again. Now you've got the upright soda can. If you just start chopping down, you get random slivers. But now if you chop this across horizontally, and in this one it would have been a vertical line that would have been its axis of revolution. So in all of these cases, cutting across the axis of revolution, all of these are what we were calling, again, the chop technique in section 5.2. So, just trying to give a little more understanding to realize how you're setting up chop. And then after we finish this video, we'll do a nice little, we'll put all this together so we know and how we know which technique is which. But these are the ways that you're getting chop, going perpendicularly across the axis of revolution. And you literally have to chop, in this case, as far left to as far right. That's how we set up our bounds in this situation, that this would be the x coordinate A, that this would be the x coordinate b, that with chopping in this way, delta x would be our thickness, and we would end up with this type of integral. Over here in this situation, you would have to chop the whole thing, but now you're not chopping left to right, you're chopping from the bottom to the top. So now we would have y values. This would be y equals c, the top would be y equals d, that these chops in this direction would have delta y as its thickness, so that this integral would be an integral from c to d with dy for its thickness. So bounds in terms of y, any variables inside in terms of y, all that comes from delta y for its thickness. In this one, bounds are in terms of x, any variables inside would also have to be in terms of x because of the dx, the delta x, for its original thickness. The last little thing that I want to mention before we get into the new technique is that if you follow the book too closely, and the same warning goes, if you look at some, I've seen some, I think they're the Shams outlines for calculus books, and some other little explanation, little calculus books, they try and make these hard, rigid formulas, pi g of y squared, pi f of x squared. But if they ever use those formulas, they are always also assuming you're just rotating around the x-axis, using the axis of revolution as the y-axis for this setup. And we've already seen, not too many examples, but we've already seen examples that were not always just going around the x and y axis. So that's why for both of these, whether it was a disk after we made these chops, so we just had a pi r squared for the area, or if we had a washer because we had that empty space in the middle, so we had pi cap r squared minus pi little r squared, that's why I stopped my formulas there. Because depending on which axis, what our axis of revolution is, that could really influence a lot what those r values are. So again, we saw all that in the 5.2, especially the video where we started to actually start solving some problems, but just some good reminders. Now let's get into the formal 5.3. So all this again, this is 5.2 reminders. So now we're starting 5.3. But we're still going to start with an ideal scenario. So I'm still going to start in a similar way that I was right here. And then again, my pictures I hope are okay, but there are definitely some good three-dimensional pictures in the book to help you visualize this. I believe it's pages 378, 379. You start to get some very good visuals to help. But before we get too crazy with that, just a nice simple picture. Let's take that nice upright cylinder that we were looking at here. If I have, that is my figure. There is my nice upright cylinder. So again, my soda can, and it's just sitting here on my desk. So as we pointed out up here, if you want to chop it, you would have to cut across the axis of revolution. That would form horizontal chops, and then delta y would end up being your thickness. We've already seen that means sometimes we have to do a little bit more to find the y bounds, to put our functions in terms of y. So that alone, if for a lot of people, is why this technique is not always the best. Not to get too far ahead of myself, but for some people, this is a technique they visualize a little bit better. But to really use the chop technique, you have to be prepared for both y or x to be your thickness, and then therefore your variable, and put the rest of the integral in terms of that variable. So an alternative, instead of chopping that into those smaller cylinders, we can peel it. And I've seen a couple other people call it slice. I don't like to use that word because slice and chop could be misunderstood. So I prefer the idea of peel. And this idea is kind of like, don't chop through the whole thing. Just take your knife, make a little cut on the outside edge so that you can kind of grasp the outer edge, and then unpeel it around the entire figure. So this is kind of like if you have a water bottle and then you've got your label on the outside of the water bottle. You slice vertically, and now you can unravel that water bottle. I could do that same thing with folded papers. if I have some folded papers like this, I apologize, I can't stand it upright in my fill, so I'm lying it down, but here's my cylinder. I've got my roundness in this direction right here. Here's my cylinder, it's just lying on the table. I make a slice down on the side, and I can unravel one piece. And this sheet of paper, that is my resultant piece. I still have more cylinder left here, but I've taken off one piece. So, how can I get the volume of the entire figure from that? Well, don't just slice and peel off one piece. You slice and peel off this outermost edge. So now I move in after that, and then I slice and I make another peel. And then I slice and I make another peel. The interesting thing here, before we get too deep, is that unlike chopping, where when you were chopping, you had to chop the whole figure from bottom to top or from left to right. But when you peel, by the time you've peeled off to here, to the middle, when you peel, you don't just peel on one side, the peel comes off the whole cylinder. So by the time you peel to the middle, this other half is already gone. So in this scenario, this would be my A, and this would be my B in terms of my X variable. And the last thing is just like this. In these perfect situations, each of these, when I chop them, are little cylinders. I could find the volume of each one, add them together to get the volume of the total figure. But in this case, what I was just showing you with the paper, when you make this first slice mark and peel it off, even though you start off with this round figure, do you notice you get a rectangle after you peel it off? That's why I showed you that example with the papers, because that is such a good view. Let's see that again very quickly. So here's my cylinder, and all I did, I just took my papers and just wrapped them around, and I'm leaving them a little loose so we can see the hole. So here's my perfect cylinder. Make my slice, unpeel, and this rectangular sheet of paper is the resultant piece. So even though it started with roundness, when I unfold it, now, I mean, it has some thickness to it. It still has, again, I'm drawing it like it's just a flat sheet of paper, but technically even the sheets of paper I show you, they have a little bit of thickness. I just can't do a good job drawing that little bit of thickness here, but there is a little bit of thickness. These marks, those vertical marks here, that thickness would still be from here to here. That's a change in X value. And then my next piece, the thickness would be from here to here. So that would be a change in X. So I still get delta X would be the thickness if I peel in this direction. In a few moments, we'll point out if I peel the other direction, if I've got this kind of cylinder, well, now I'd have to make horizontal peel marks, and that would make delta Y my thickness. So we'll still have that possibility, but let's finish this before we get too crazy here. What is the volume of this rectangular slab? Well, it's kind of, again, it's a thin piece, but it's just like a book. If you're looking at a textbook, how do you find the volume? You get the area, and that's the area of a rectangle, so you'd have your base times height, and then you'd have your thickness over here as the extra dimension. So the delta X as the thickness, I need the area. And over here, I'm calling this side the height, and the height here directly corresponds to the height here. I made the slice, I unraveled this and peeled it, but this distance here still corresponds to this distance right here. It is a perfect match. But what about this side? This side, the length or the base of this rectangle, we'll go back here. Where did this come from? This came from putting in this slice and peeling this around the entire roundness of the figure. The base here is actually equal to the circumference back over here. That this roundness across the bottom, that when I peel this slice and open it up, that this total circumference ends up being the total length of this side. So circumference of a circle, we could either use pi times d, but we typically tend to use 2 pi times r. So I get volume of this first piece, the area, base times height, times the thickness. So the volume of just one piece ends up being 2 pi r times the height times the thickness. So I've got delta x again from this first example, but just to make the note, that could also be or delta y in the right situation, in the right circumstance. And that's just the volume of one piece. I'm going to find the volume of all these slices of all of these peels, add them together. So I'm going to do the summation of I 1 to n. N is how many pieces. And I've got this set up, the 2 pi r h delta x or delta y. But this is only going to give me an approximate. Because this one, well, this is perfect. This already was a perfect cylinder, but now just start to realize, now thinking about the reality of calculus, that if I had a figure that was more like this, if that was my initial trapped region, and if I revolve that around the y-axis, this would flip to here. The initial construction is still exactly the same as we had in 5.2. We're still going to be given a bunch of curves that we could make this trapped region. We should shade it in, revolve around an axis that would be given as a part of the problem, and we'd end up with this type of shape. And this, again, this is like a big open bowl. If you really understand how we're flipping this around, this is a big open shape that would have maybe, it's your fruit bowl that you have up front. It's got a little bit of a thick side on the bottom here. But again, it's completely solid as you go around. And from the bottom, you'd hit a little bit of a bottom if you tried to, enter from the bottom. But from the top, there is this open space that you could, pour in liquid, put in fruit, or whatever, something along those lines. So now with this setup, now I would make my peels just like we were saying here. So with this direction, already start to notice, if you are peeling, you cut in the same direction as your axis of revolution. Up here, when we reminded you about chopping, you cut across the axis of revolution. That's how you get the nice discs or washers, and that's why that technique works. But down here, with this new technique, you peel in the same direction as your axis of revolution. So I make this peel mark here, but then this side also comes off. I make this second peel mark here, but then this side also comes off. Remember, it's not a flat object. This is three-dimensional, so again, this whole outer edge comes off the whole figure. So that's set up. That's again a delta x. Now I'm not getting these perfect peels. Again, we'd have to still flatten these out a little bit. Just like up here, we had to flatten these pieces a little bit. And now, how do we make this perfect? How do we go from approximate to exact volume? By making more peels. Not just making 3 or 4 peels, letting the number of peels approach infinity. And here's the last really nice part. I know all this is tough. We said this right at the beginning of all volume. This is not an easy section. There's a lot to try and visualize. The formulas help, but you can't just blindly try and plug into formulas. You got to have some understanding. You got to be able to visualize a little bit, but something that's nice. Come back to this shape. If you were going to chop it, you would chop across, and then you'd also have to realize that with this empty space, that this would be a washer and not a disc. But when it comes to peels, that is completely irrelevant. This is empty space, it's filled in. Well, it's filled in down here, it's empty up here. It doesn't matter. When you peel it, well, over here, these peels on the edge, their height is much taller, and these peels in the middle, they've got a very little height, a very small height, but that doesn't matter. they're still all just peels. So this, we're not getting two possibilities. We're not going to get two volume formulas like we did for chop, where we had to decide again, disc or washer. All of these would be volume by peel. And again, that definition becomes the definite integral a to b 2 pi r h dx, or I'll use the same notation, c to d 2 pi r h dy. Now, I've kind of hinted a little bit about this. You are going to get to pick which technique you use. I think it's very important in the beginning to get practice with each topic, but you'll see as we move on and we get to our next review video and put all this together, we'll start talking about what works best for you. And for some people, they prefer working with X. So they will always apply the technique that gets them to X. It's the variable we're more comfortable with. It tends to work out a little bit easier. So it's always just, I want to make dx my thickness. And that's what some people prefer. Other people prefer, typically, they tend to prefer, if it's just one technique over the other, they prefer the chop technique. So that they will always chop, but if you chop, you have to be prepared for both delta X or delta Y. So there's kind of a little bit of a pro and a con that go with both technique. So once again, let's get good practice with both technique individually. Let's go through the individual homework, take our time through the videos, see the examples, but then again, realize we're gonna come back with a video that puts all this together. And we'll try, even today, we'll do a little comparison, but we'll have a whole separate video that starts to look at, well, you could use either technique, but which one is better? Which one would end up working out a little bit better for that situation? Okay, so that's our situation. Now let's already jump in. Let's take a look at our first bunch of examples. So all the examples for right now, I'm gonna use the same basic set of curves. And like I said, we'll make a few points. There's still, even if you understand the formula, there's still a few little nuances that definitely bug people with these little setups. Finding R, finding H. So again, let's take our time and let's see what we have. So, directions, just like the other day, we are going to generate a figure, a solid figure, by revolving the trapped area around a given axis of revolution. And just like the other video, we are really going to focus on the setup. Setup integrals that represent the volume. So we're going to generate these solid figures, and then that's our main direction. We're going to actually set up the integrals. The first one I'll go through and solve it completely, but then after that, I'll just make a few points, but we'll really again focus on the setup. So let's start off, number one, we're given the curves y equals, let's go x squared plus 1. We'll use x equals 3, x equals 0, and y equals 0. Those are my curves to give me my trapped region, and we are going to revolve that around. Let's start with the y-axis. So, we've got to start, get our figure drawn. Okay, again, we need something. So even if you're not great with curves, graphing calculator, just getting yourself something. Even plotting a few points can really help. So x squared plus 1, that is a parabola, bumped up 1 unit. X equals 3 is a vertical line somewhere out here. So that would be my x equals 3 line. X equals 0 is the y-axis. Y equals 0 is the x-axis. So put all those together, And this is our trapped region. Now, we take that trapped region, revolve around the y-axis. So all this flips up out of the paper, back onto the paper. I like to draw the two-dimensional reflection. And again, just like I said for 5.2, for some people that's enough. Your initial area, seeing the reflection. Some people literally just having the initial area and where they're turning. Some people get away with that. That's enough. I think most of us do better with this. And if we can just get a little bit of roundness to remind ourselves the three-dimensionality, that'll help. And this really does not look all that different from this shape we were just discussing a moment ago. This just has more of a base, okay? It has a big solid flat base, and then up here it's got this little extra empty space, but completely solid all the way around. So this, honestly, this is like maybe like a mold for a bullet. We've seen a couple of bullet-like shapes. Here's the bullet, but the bullet is the empty space, so maybe this is the mold, and this is where you actually form your bullet. But in any case, this is where we start. And I really want to focus on the new technique, but I want to show you something very quickly with our old technique. If you want to chop this, you cut across your axis of revolution, and now you're chopping. But if you're chopping, well, delta y would be your thickness. You're going to need to make some little adjustments to the curve. When you end up, again, you need your variables will have to be in terms of y, not x. But do you notice a bigger problem? Or maybe not exactly a problem, but just something extra? If you chop, do you have discs or do you have washers? The answer is you have both. So again, this is what I mean. Either technique, any problem I give you, at the end of this video, I will show you that you can't, in the grand scheme of things, you can't use any technique you feel like. There are a few little restrictions, but for any problem that I give you, either technique will work, but sometimes one technique might be a little easier than another. Again, if you do this one, look down here. If I make my horizontal chops, everything from one side to the other is solid. So from this point down, these would be completely solid discs. So you'd have to make an integral just based off that. But then when you're up here with these chops, well, you've got filled in, but you've got this empty space in the middle. So you'd have washers up here. So you need two definite integrals. You can't do that at all the same integral, so you'd have to do two. An integral from here to here in terms of y, and those would be solid discs, and then a second integral from here to here, and that's where you would have washers. So we can come back and take a look at that. And like I said, when we do our full review video, we'll take a look at several problems doing them using both techniques to give you a better sense of what you prefer. But for right now, again, nice to bring that up, but now let's focus on the new technique. The vertical axis here, I'm going to take my red pen and I need vertical slice marks. And again, I'm not doing 3 slices on the right and 3 slices on the left. By making these 3 slices on the right, make this slice, peel it off, this is coming off the left side. Make this slice, peel it off the whole side, this comes off the left. Make this slice on the right, peel it off the whole side, this comes off on the left. See, I'm almost saying left and right, but we still have to keep remembering 3-dimensional figure. So again, page 378 is kind of the inverse of this. It's bigger up here and lower on the sides, but they do a very nice job of kind of showing you all those little peels that they're making and how they still all give us peel. Don't have to worry about disc or washer. It's always a rectangular peel. So that's the beginning. Get your picture set up, establish your technique. Now think about your thickness. The thickness sets the rest of the stage for our bounds and our variables. So our thickness, these vertical marks here, makes this my thickness. this my thickness, this my thickness. Changes in x values, so delta x for the thickness. My height, well, my height, this over here, go back to the original picture, that corresponds in my first peel. This height would be from here to here. The second peel, my height would be from here to here. From here to here. I'm going from the x-axis to this curve every time. Technically, we did all this in the first video, that is the y value. But I need the y value in terms of x, so h is x squared plus 1. Okay? And now let's take a look at the base. The base is always 2 pi r, but what is r? And this is where so many people get frustrated with the peel technique. H isn't too bad. H in a lot of ways is similar to how we found r in the chop technique, but now finding r here. R. Now I'm back to r, so I have to have some sense of what is in the center. And the axis of revolution is in the center. So my r, well, my first peel would be from here to here. That would be r. Then in my second peel would be from here to here. Notice I'm not using the curve. I don't need the curve, I just need the line. So I could say from here to here, but that is the same as here to here. And my third one, here to here, would be my last r. It's a changing value. It's especially tempting when I do the first one. When I go here to here, people say r is 3. And that very first peel, you are correct, because you're starting at the y-axis. This is the line, x equals 3, so that first r is a distance of 3. But then the next one, r is shorter than that, and then r is shorter than that. So it's not r is just 3. What is r? Every single time, what am I doing? I'm just going to an x value on a point. This has an xy pair, this has an xy pair, this has an xy pair, but every single time, the x coordinate is the value of r. So all that to just get r is just simple x. Now that's still frustrating, so we definitely want to focus on that in the next couple of examples, but I also want to point this out. For some people, this really helps them. If you're revolving around the y-axis and you are peeling like we're showing here, you're using the cylindrical shells technique and peeling. If you're revolving around the y-axis, r is always x. But outside of that, go around any other line, and now you've got to make adjustments. But it'll need x as a part of that. So again, you'll see what I mean as we do more examples, but now let's finish this one. Because now we've got everything set up. So I've got the integral of 2 pi r, which is x, times the height, which is x squared plus 1, times the thickness delta x, which becomes dx. How about my bounds? Again, go back. It is very easy to mistake and say, okay, I peel from here to here, and I go from -3 to 3, but that is incorrect. You're only peeling half the figure. You peel this off, this comes off with it. You peel this off, this comes off with it. So by the time you've peeled to here, this is all gone. So where am I peeling in this one? Just from here to here. Now, technically, we'd be going backwards from 3 to 0, but we always want to set our bounds up from left to right, so our bounds would be 0 to 3. That is the setup. That is, again, what we're going to focus on for the most part, getting used to the formulas and being able to adjust the formula for whatever problem we are looking at. That's what we're going to focus on for the rest of this video. But just before I do that, before we keep rolling into more examples, let's solve one of these. How would you solve this? The 2 pi, most people, again, just like to kick it out in front, and we'll take care of that at the very end of the problem. Just that nice little multiplier, the pi included, just jump that out in front. But inside the integral, we've got a little problem. Nothing major. I mean, there's addition between terms, but right here, the fact that it's x times x squared plus 1, there's a little bit of an issue with multiplication. There is no product rule for antiderivatives. So how do we deal with that multiplication problem? We multiply. X times x squared is x cubed. X times 1 is x. And now there's no more multiplication problem. So now I can take my antiderivative. Every time we finish an anti, something comes at the end. This is a definite integral, so we get the bar and the bounds. And now I'll plug in my bounds to finish. 2 pi, plug in 3 to the 4th power is 81, so 81 over 4. 3 squared is 9, so I'll get 9 over 2. Minus, and I'd still have another 2 pi or a big bracket, but now I'm plugging in 0. But 0 to the 4th over 4 plus 0 squared over 2 is all just a big 0. Now, if you want to get a common denominator, clean that up, some decimals, a lot of different options here. But that is a good, clean, correct final answer. Again, the book would definitely get a common denominator. This is just another little instance. Sorry, right here. So I did my antiderivative, plugged in the top bound, minus, plugged in the bottom bound, but that was all just 0. You know, again, the book would get a common denominator. That would be 18 over 4. So that would be a total of 99 over 4 times 2 pi. So that would be 198 pi. Actually, no, I'll cancel. I'll cancel the 2 and the 4. So I'll get 99 pi over 2. And that's almost certainly how the book would leave their answer for this one. So, just a quick reminder on solving. You do want to get some practice solving, but like I keep saying, even though there are formulas here, the disk washer method, you just often have to clean up the r squareds before you can actually solve the integral. Here, you always get this idea of 2 pi r times h, so you have to do this little bit of multiplying, and then you could take a straightforward antiderivative. That's pretty much the situation we're going to be in. Again, are there ones that could be hard that would need U subs? Yeah, but nothing that we're going to look at. The ones we will look at will really be maybe the most minor U sub, but really should just be a matter of just cleaning up by hand, doing the multiplication, doing the squaring, and then moving on. Okay, so I want to stop here. We'll start another video, and we'll continue with more of these problems, get more practice with this peeling technique.